Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to finally get into some aspects of astronomy that have been around us for a long time, and that is the nature of the spectra of stars. So the stellar spectral types and how we interpret their spectra. That's the beginning of the understanding of the nature of what stars are, and so let's talk about that right now. Well, what are stellar spectra? If you take the light from a star and you break it into a prism using a spectrograph or something, you take the light from a star, put it through some sort of slit, let the slit then go onto a prism or in a shell spectrograph or something, you'll break apart the light into a rainbow color. And every single kind of star has a unique fingerprint, not unique, but I mean unique for its type. And so different stellar spectra have different appearances. Now, it was thought for a very long time that these things were all very random, but yet patterns were discovered. And it's the discovery of those patterns that we'll be talking about today. So the types of stellar spectra we see here in this diagram show us that we have various kinds of spectral types. On the left-hand side is the spectral type running from O to M with a couple of others at the bottom, and then the catalog listing. Now if we look at the spectra, these are photographic color prints of the spectra, and we can see that the blue side there's a blue end and a red end. And we see that for the O-type stars, they're significantly brighter in the blue than in the red, and for the M-type stars, they're significantly brighter in the red than the blue. We also see kind of a gradual progression of dark lines in the spectra, meaning absorption lines that appear inside of each of the spectra. And they change with spectral type. So let's see what all that means. All right, so first and foremost, stars actually do have color. So if you go outside into a dark night and look at stars, if you look at, say, Albireo, which is Beta Cygni, and you go and look at it through a telescope, what you'll find is that those two stars in the sky, actually it looks like one in the sky, but if you look at it through a telescope, you can resolve them into two. One of them's gold, one of them's blue, and so stars have color. They definitively have color. So stars are basically big, hot balls of gas. They're just the same thing as the sun, except really far away. And when we look at some star that's very, very, very far away, we notice that it has a certain color. Stars themselves, because they're hot and big and dense, they're huge like the sun. The sun is 1,000,000 times bigger in volume than the Earth, and 100 or so diameters across, Earth diameters across, so they're really big. Anything that's really hot and really dense emits a continuous spectrum. And the continuous spectrum comes from below what we call, from the photosphere, the lowest visible layers of the star. And that spectra is really close to a black body, which can be described with a single temperature. Now, if a star has a black body spectrum, then from Wien's law, which we talked about some time ago in another video, from Wien's law we expect that hot stars appear blue and bright, and medium hot stars will appear yellowish, and cooler stars will appear red. So, well, let's go look. So we'll go back and look at Wien's law. So what the heck was Wien's law? Wien's law showed that the peak wavelength at which a black body radiates is inversely related to its temperature. So the hotter it is, the shorter the wavelength. The cooler it is, the longer the wavelength for the peak of the black body spectrum. This means that if we look at extremely cool objects in deep space, such as dark molecular clouds, they'll be peaking way out in the infrared, and their temperatures will be very cool. So they'll have long wavelength light that they'll be emitting mostly at, and their temperatures will be very low. When we go up to like solar type objects, the temperatures are relatively high, about 6,000 or so Kelvin, and the wavelengths are roughly in the range of about 5,000 angstroms. So that's invisible light. So these are shorter wavelengths than infrared. And if we go to extraordinarily hot objects, such as X-ray emitters, they can be emitting primarily out in the X-rays or in the far ultraviolet, and that would be a very short wavelength, but the temperatures are then very high. So Wien's law just simply says that the peak of the wavelength of a blackbody spectrum is inversely related to its temperature. All right, so the spectra of stars then are determined by the peak of that blackbody spectrum, or at least the fact that there is a blackbody spectrum below an atmosphere of the star. So the star isn't like a solid object and here it begins and there it ends. No, we've seen from the sun, if you look at an eclipse, that the sun has a photosphere, the sun has a chromosphere, it has a corona, it has a solar wind. All of the materials of the sun come off of the sun as a solar wind. So there is an atmosphere to the sun. So likewise, there is an atmosphere to every star. And that atmosphere is by definition cooler than the interior of the star. So it's absorbing the light and re-radiating it at other locations. Well, that produces an absorption line spectrum according to Kirchhoff's laws of spectroscopy. So we can use, or at least we think we can distinguish different kinds of stars from their spectra. So when people were first invented photography, way back in the latter part of the 19th century, people were looking at the stars, taking pictures of the stars, taking spectra of the stars, because what the heck, why not take a spectrum of a star to see how bright it is at various wavelengths? And people made catalogs, huge catalogs of stars. So the spectral classification of stars happened well before photography was invented. It started in the 1860s by a Jesuit astronomer in Italy who observed with a prism just to his eye about 4,000 stars or so, and he divided them into 4 rough groupings, and he found that there was common spectral absorption features, meaning dark lines that he could see. So he was doing this all by eye with no photography, and it's very interesting that he was able to group them into various things. So that's 1860s. Between the 1880s and 1890s, the Henry Draper Memorial Survey at Harvard University, it carried out a systematic photographic study of all the stellar spectra over the entire sky. This was an enormous, enormous undertaking, effort which was led by Edward Pickering at Harvard. So this took at least a decade or plus to actually make all of these things. They used objective prism photography, and remember the photography was invented in the latter part of the 19th century, and so using prism photography, he was able to take from the telescopes both at Harvard University and down in Peru. They obtained about 250,000 spectra of 250,000 stars. And what they then did is they said, well, we're going to take all these spectra and we need to organize them. I mean, there's 250,000 for goodness sakes, and it's going to take a long time. So what they did is they hired a series of very intelligent women as computers. That was their job title, a computer. And their job was to analyze these spectra. So the women got in a room and started working on it, and Edward Pickering hired a large number of women to do this analysis. And in 1890, Pickering and Wilhelmina Fleming started their first attempt at spectral classification. First, they sorted the stars by the hydrogen absorption line strength. So they looked at how strong the hydrogen absorption line, and they said, well, the A stars have the strongest hydrogen absorption lines, and they went farther and farther down with weaker and weaker hydrogen absorption. So that was mainly their goal, was just to organize them by hydrogen absorption. The problem is that as it got weaker and weaker, there were other lines that kind of just magically appeared, and so deciding which lines to actually classify them by, because you started with A, B, C, D, E, F, and just say, well, they get weaker and weaker, but then other lines start protruding in. So therefore they knew that they didn't have the final answer, but they didn't know what the answer really was, and their best guess was the hydrogen absorption line. So that's what they stuck with. But rearranging those spectra was a major undertaking. And approximately 11 years later, in 1901, Annie Jump Cannon noticed that the stellar temperatures were the principal distinguishing characteristic among the spectra. So what she did is she took all this arrangement, the A, B, C, D, E, all the way down, and she rearranged them. Instead of by hydrogen absorption line strength, she removed most of the classes as being redundant, and she reorganized them according to decreasing temperature. So she found the O stars to be the hottest temperature, then the Bs, then the As, F, G, K, and M. And these are the 7 primary stellar spectral classes that we recognize today. It was an enormous undertaking that she did, and this reorganization was enormous. Later work she added, there were other stellar classes like R, N, and S that were later added, but those have been recently discarded and no longer used. But we use different types instead today. But her organization of these things in 1901 was a major undertaking, and it actually gave us significant understanding as the nature of stars. So when she published her catalog of stars in 1901, it was she was then considered one of the most influential astronomers of the 20th century. And she is definitively one of the most important astronomers of the 20th century, primarily because she had access to the data and she knew what to do. And she did something that no one else had done with enormous undertaking, with enormous data sets, and discovered something truly fundamental, which was that the stellar spectral sequence is a temperature sequence. That's the trick. So you can organize them from O stars as being hot to M stars as being cool. And she used basically Wien's law to do it of blackbodies. She lived between 1863 and 1941. And she eventually, over the course of her entire career, classified over 500,000 stars. So, wow, that's a lot of work. 500,000 of anything, of any activity, is a very hard thing. If you suspect, just put it together, just do it in your head and think, imagine that it took 1 to 2 minutes per classification. And if it's, just say 2 minutes just because. She was faster than that, but imagine it took on average 2 minutes. So that ended up being 1,000,000 minutes of stellar classification throughout her entire career. Wow, just astonishing. There's a reason why the Annie Jump Cannon Award for the American Astronomical Society is one of the most prestigious awards that one can be bequeathed for lifetime research in astronomy. All right, so her stellar spectral sequence was incredibly important, and we cannot overstate its work. It classified them from O's, which are brightest in the blue, to M's, which are brightest in the red, comparatively. And when she looked at them, she was able to determine that the temperatures of the stars ranged from about 50,000 Kelvin in the O's all the way down to about 3,000 in the M's. Well, what she then did further is that between about a decade later, she created subclassifications. So she further divided each stellar spectral class into subclassifications, such as with a number at the end from 0 to 9, and these things were gradations of A star. Let's say we start with an A star, and so the highest temperature A star was an A0, the lowest temperature A star was an A9. And she took another 13 or so years, applied this concept to the Harvard classification scheme to about another quarter million stars, and this was then published as the Henry Draper catalog. Henry Draper, why not Annie Jump Cannon? Well, Henry Draper was the one who was running the program at the time, so it became the Henry Draper Spectral Classification System, and this system has been adopted by pretty much every astronomer globally, worldwide, as the way to classify stars. So it is a global standard for everyone, and it allows astronomers to talk to each other about the types of stars, what they are, and how they're classified. And this is a very important undertaking, and it's recognized worldwide as being an incredibly important thing. All right. So now we look at the stellar spectral classifications individually, and we say, well, why are all the absorption features different? What's the reason for their difference? Why do they exist? Why do these stellar spectral classifications even exist? So it was first thought that the composition of the star was the thing that determined the absorption. Because that makes sense. If you put, say, sodium in a Bunsen burner and look at the gases that come off, you see emission lines of sodium. And so likewise, if you took a very, very, very hot source of light behind the sodium vapor that's coming off after it glows and it's just floating upwards cool, you'll see sodium absorption in the hot light as on top of a continuous spectrum. So it's totally natural to think that the absorption lines in a star would be directly related to the composition. And that's what was thought for a very, very, very long time. So therefore people thought that A stars were primarily composed of, say, hydrogen, and M stars were primarily composed, in their atmospheres at least, of oxide molecules of different elements such as titanium oxide and vanadium oxide and carbon monoxide and all sorts of other things that could be, where spectra could be obtained. However, that's wrong. And that's interesting how that's wrong. And the person who discovered that that was wrong was a graduate student. She was at Harvard too. She was one of the computers, and her name was Cecilia Payne-Gaposhkin. And in 1925, her doctoral dissertation was published as a book, Stellar Atmospheres. And it was quite literally one of the most breakthrough understandings in the nature of what stellar spectra are. she used the rising concepts of quantum mechanics, which were being discussed and debated down the hall from where she was working, and she said, well, wait a second, it's not about the composition, it's about the excitation. So every atom has different excitation levels, with hydrogen needing a huge amount of energy in order to excite the electrons out of the ground state. And so if you have hydrogen excitation, you need it to be very hot, such as an A star. But if it's too hot, then they get ionized and it decreases again. But if it's not, if the photon field isn't energetic enough, then you don't get any excitation at all, such as in the cool stars. And if it gets cooler still, then molecules can form and you get molecular transition lines. But that doesn't change the fundamental composition of the star itself. She discovered that stars were primarily composed of hydrogen and helium, and that was their stellar composition, but only the relative abundances of, only the temperature was what determined what the absorption features were. So if she assumed, and she assumed roughly rightly, that stars are roughly the same chemical composition with dominantly hydrogen and helium, then the stellar absorption features are due entirely to the temperature of the background photon field. And that was her breakthrough analysis using the understandings of quantum mechanics and how much it takes to excite atoms at various temperatures in gaseous states. So that was become one of the most important things, and it's still very good reading today, and it's a good way to actually understand the nature of stellar spectra is by reading her dissertation from 1925, Stellar Atmospheres. So that was the reason for it, and the composition is not important. It's not really the thing. It's only the difference in temperature that makes the important thing. So as some examples, B stars are the stars, the hydrogen is almost all completely ionized, so you get very weak hydrogen lines. A stars, you get the maximum excitation temperature so that they get out of the ground state, they go to the first and second and third excited state, they drop back down and they re-radiate their light in other directions. G stars, too cool. There's not enough photons. The photons are not energetic enough that exist. There's not enough energetic photons in order to excite the hydrogen out of the ground state and into excited states such that they can absorb at that frequency. So that's the reason for the hydrogen lines. And then if we go further on, we find that, well, let's jump forward a bit further in time. Right in the latter part of the 1990s and 1999, a couple of different stellar classifications were added, the L's and the T's, which are much, much, much cooler. They're cooler than the M stars. They're about under 2,500 Kelvin. And they're starting to show up radically in digital, extraordinarily sensitive, infrared, full sky surveys. They're so very, very cool that they emit mostly at infrared wavelengths, and L-type stars are between about 1300 Kelvin and about 2500 Kelvin in the light in their temperatures. They've got lots of molecular absorption, such as chromium hydride and iron hydride and lots of neutral metals, but also some strongly bound molecules such as titanium oxide and vanadium oxide. So these bands of spectra are really there. However, if you go even cooler, sub the 1300 Kelvin, you get what are called the T-dwarfs. And the T-dwarfs are really strange. They've got methane and ammonia, and they could be considered failed stars. These are the brown dwarfs. The difference between a T-dwarf and Jupiter is really fuzzy. And so that's a boundary area of current research, is trying to understand that. We don't think that most of the T-dwarfs are massive enough in order to ignite hydrogen in their cores to make them actually stars. So the boundary between a T-star and a red dwarf and a dwarf star, or specifically even a brown dwarf or a Jupiter, is very fuzzy, and it's an area that people are looking at entirely today. Okay, so go back in time again. So this is forward. Now we go back to like 1943, and Morgan and Keenan added a second level to the spectral classification system. And what they discovered is that not only did stellar spectra, the two stellar spectra could have exactly the same absorption features, except that one set of absorption features lines were wider than the others. So you could have different widths of lines for exactly the same temperatures. And what they discovered then, that they classified them into 6 general groups. We call, which there are supergiants, giants, bright giants, giants, subgiants, and dwarfs. And so those 6 classifications that we see today are based on the widths of the lines. So not only is there a temperature profile, but there's a width profile. And this spectral classification, this subclassification, this luminosity class has always added to a star if you can do it. So the Sun is a G2-5 or G2 dwarf. Betelgeuse is an M2 supergiant, or M2-1b. Rigel, another wonderful bright star in the sky, is a B8 bright supergiant. Sirius, one of the brightest star in our night sky, is an A1 type star, and it's also a dwarf or a main sequence star. Aldebaran, which is another prominent red giant star, is a K5 type star, and it's a giant type star. So these kind of things are based on the widths of the lines, and you compare them between various types, and you can see the difference. It's prominently displayed in digital sky surveys because you can get much more greater resolution. All right. Why is this all important? So we're just looking at stars and classifying them and putting them together. Well, stellar classification is probably the best way to get to understand the physical characteristics of stars. When you don't really know anything about anything, what you first do is you group them by their appearance, which is what was done initially back in the 1860s and 1880s and 1901s, and that was the goal. Just arrange them in some logical order. And all of a sudden, by arranging them in the order, you discover, hey, wait, NHL Canada said, this is a temperature profile. And then people said, wow, that's interesting, what about composition? And Cecilia Payne-Gaposhkin said, well, wait, if we look at this, then we take the physics on top of that. Those arrangements of the stellar spectra are based on the physics of quantum mechanics and how atoms react with each other. So the spectrum uniquely identifies the star, because you can look at thousands of stars, and they've looked at hundreds of thousands, and hundreds of thousands have been classified. And we find that they fall into these groups. There's nothing else besides the O, B, A, F, G, K, M, L, and T's, and anything like that. They are the primary classifications. They can be put somewhere in there. There's no other real weirdos. We can call carbon stars weirdos or white dwarfs weirdos. But other than that, we really can't say that there's anything that's like, oh, that's a star, but what the heck is it doing? It's only emitting at one wavelength. That would be really weird, and it doesn't happen. So there's something fundamental that it tells us about the star. We learned that there are opaque hot bodies with an atmosphere above them with absorption lines, and we now understand the process of that. So stellar spectral classification is the first, most basic tool, and it's incredibly important for understanding the physics of stars. All right. So people come along for a long time and they say, well, let's find out how we can remember this, because undergraduates in astronomy have been trying to remember O, B, A, F, G, K, M for a very long time. And you can come up with all sorts of funny mnemonics, and some of them are good, some are bad, some are PC, some are not so appropriate today. But if we look at the old ones, say from Harvard in the 1920s when they became it, and it was, time is, oh, be a fine girl, kiss me, or oh, be a fine guy, kiss me, whatever you have. But people have come up with new ones. My favorite that I came up with is Overseas Bulletin, a flash, Godzilla kills Mothra. I like that one, that's fun. And there's all sorts of other ones. You can make up your own, lots of different things, and if you post them on the YouTube channel, that would be cute. So make up one, post it here, I'd love to see it. All right, so let's look at these stellar spectra specifically, and look at specific examples of stellar spectra. So let's start with the O stars. We find that they're so very hot that they peak in the ultraviolet, and in the survey that I'm looking at, this comes from the Sloan Digital Sky Survey, and I'm looking specifically at data release 5, and I'll look at a few spectra from data release 5. So we got the O stars, they're so incredibly hot, they peak in the ultraviolet, and they peak outside the range of the spectra of the stellar of STSS. And that means that we have very strong helium ionized helium lines, and the temperature is over 30,000 Kelvin. And hydrogen lines don't exist. Why? Because all the hydrogen ionized, so you can't get absorption if you ain't got an electron in the atom. So that's why you don't get hydrogen absorption in O stars. Now if we look at B stars, we start seeing hydrogen absorption features, but they're weak. And then you also have some neutral helium, because helium is strongly bound, but not as strongly bound as hydrogen. And so we get neutral helium as opposed to ionized helium, and the lines of hydrogen get stronger and stronger until we get to the A stars that are cooler now. Now we've cooled down to about 10,000 Kelvin, so you get very, very, very deep absorption features in the due specifically to hydrogen in the stellar spectra of A stars. When we get to F stars, the hydrogen absorption starts to get weaker because the temperature is cooler, so you have fewer photons to excite the atoms of hydrogen into upper states, and that's right around 6,000 to about 7,000 Kelvin. Hydrogen is weaker, and you start to get ionized calcium lines, and they start to begin to emerge because they're the next thing that's easy to ionize. That's interesting. And then when we get to G-type stars, which is the sun's a G-type star. The peak of the curve is now firmly in the visible range at approximately 5,500. And there's strong absorption features due to hydrogen and calcium. Well, not so much hydrogen anymore, but we have singly ionized calcium, and then some other metals start to dominate. Metals here being anything other than hydrogen in the lines, or helium. But we start to see that that mostly important is the peak is in the middle of the visible spectrum. We see K stars even further over into the red side of the spectrum, and finally we get to the M stars, which are extraordinarily cool. They peak way out in the infrared, much past the visible wavelengths. They peak out so far in the infrared that they start to peak around 10,000 angstroms or so, and then they kind of cool off. And some of the late type M stars even peak much further. When we get to the L type stars, there's practically no emission in visible light, and you have to actually look for them in infrared, and you see lots of molecular absorption. You see there's almost no emission anymore, no absorption due to very strongly bound atoms such as titanium oxide and vanadium oxide, and these things are very, very cool stars. And if we go to the T-dwarf stars, or the brown dwarfs, you see molecular absorption due to water, due to methane, due to ammonia. These things are like Jupiter's. That's exactly what they are. So these are the failed stars. They have very loosely bound molecules that can easily be destroyed if the star was hotter, but they're not, so you have a T-dwarf star. And so this is boundary zone, and they're very interesting to study because where do stars end and planets begin? That's an interesting question for astronomy. All right, so as we see, the stellar spectra are an incredibly important element of all of this, and as we look at the types of stars that we have in the sky, we can classify them to this stack of groups. And the stack of groups ranges from the hot O stars to the cool M stars, and as we look at them, we understand the nature of their atmospheres, we understand the nature of their temperatures, and we get to begin the physics of stars. And that's what we'll pick up next time. See you soon.